Hello. In this video we're going to be looking at the concept of density, what it is, how you measure it, and how you measure the density of things that on the face of it might be quite difficult to measure. So starting off with density, we use the word density. If I was to say to you what's heavier, cheese or wood, for example, we could find out. I have got here my kitchen scales. If I just turn those on here, and that's on a 0. I've got a piece of wood here. My piece of wood, that weighs 35 grams. 35 grams, and if you can see that. And then I have a piece of cheese here, and this piece of cheese that weighs 30 grams. So you can say quite confidently that wood is heavier than cheese. Except you can't, can you? Because there's something wrong here, and we've got two things that are different sizes. So if I really wanted to ask the question, is cheese heavier than wood or is wood heavier than cheese, I'd use the word density. Is cheese denser than wood? And so to make this a fair test, we'd have two pieces the same size, which I've done here, and so my cheese weighs 30 grams, and the piece of wood, which is the same size, weighs 15 grams. So you could say that cheese is twice as heavy as wood, or being more correct about it, it is twice as dense as wood, because density is how heavy something is compared to the size that it takes up. If you have two things that are the same size and you weigh them, you're comparing their densities. So to calculate density, you need to know two things. You need to know we talk about mass, but we really should be, so we talk about weight, but really should be talking about mass. So you need to know the mass of something, and you also need to know its size. And when we talk about size, we're talking about volume, which is how much space it takes up in the room. So the density is the mass divided by the volume, and the volume is very straightforward to measure. If you've got something sort of squarish shape like this, we could get a ruler and say this piece of cheese is 3.5 centimeters one way, 2.5 centimeters the other way, and 3 centimeters the other way. So you could say it's the volume is 2.5 times 3.5 times 3 centimeters, and you would get an answer of a certain number of centimeters squared. And you know the mass, and the mass was 30, and so you could work out the mass and divide it by the volume, and you end up with your density. Now, with all of these things, all measurements in science, you need to be careful about the units that you use. Now here we're talking about grams, which is measuring on my kitchen scales here, and centimeters, and from that we work out centimeters cubed. But really we should be talking over here about kilograms per cubic meter, not how many grams per cubic centimeter. And it is a little bit mathematical, and science is mathematical, but you need to sort of be calm about this and look at it, and you can convert one to the other. So if you look at this, if you had 1,000 grams over here, you would know that that is a kilogram. So if you had 1,000 grams, that's easy. You can say that's just 1 kilogram. But if you had 100 grams, you'd say, okay, that's not quite so straightforward. That is 0.1 of a kilogram. 10 grams is 0.01 of a kilogram, and 1 gram is 0.001 of a kilogram, which is 1,000th of a kilogram. And then you've got to think about, can you convert cubic centimeters into cubic meters? Now we all know that there's 100 centimeters in a meter, but how many cubic centimeters are there in a cubic meter? Now here's a cubic meter. It's got 100 centimeters along the bottom, 100 centimeters up the side, and 100 centimeters the depth of the thing. So that is 1 meter by 1 meter by 1 meter. So that's 1 cubic meter. But if you were to measure the volume of this in centimeters, you've got 100 by 100 by 100. 100 by 100 by 100 is 1 cubic meter. Now if you do that sum, it actually comes out at 1 million. So 1 million cubic centimeters is 1 cubic meter. So we'll do the maths another time, but just bear that in mind when you do things like that. Now, so it was quite straightforward to find the shape, the volume of a regular shape thing like this, that's a rectangular shape. You can just measure things. Now if you had something that's of an irregular shape, like this stone here, it's not so easy to find the volume because you can't just measure the shape of the sides, because the sides are all uneven. And we go back 2,200 years to a man called Archimedes. And Archimedes was a very clever scientist who was given a job by a king of Syracuse in Sicily, who suspected that he was being conned by his crown maker. Now, he would give his crown maker a certain amount of gold and say, I want you to turn this into a lovely crown for me. And he'd get the crown back, and he'd say, I don't know if this is all gold. I think he's mixed a bit of silver or something like that in silver, which isn't quite as heavy or isn't as dense as gold. But I can't really tell. I gave him a kilogram of gold. He's given me a crown that looks gold, and it weighs a kilogram. But I think, well, the king thought he'd taken some of that gold and for himself, and added a bit of silver and mixed it up and melted it and made a crown. So he gave it to Archimedes and says, I think I'm being swindled by this guy. What can you do? And Archimedes thought about this, and he thought, well, I know the density of gold, and so if I could measure the density of this crown, but then that would mean me melting the whole crown down into a lump, so I could measure the size of it, and that would be no good to the king anymore. And then he was sat one night in the bath, and as he sat in the bath, he got in the bath and the water rose up around him, and he thought, I know how to do this, because the water that he displaced in the bath was the same as his volume, the same as his space that he took up. And he was so excited about this that he jumped out of the bath and ran through the streets shouting Eureka, which is I've got it, or something like that. That's where we get the phrase Eureka from. So he went running Eureka like a streaker down the street, and he then did get the king's crown. He put it in some water, and he measured how much the water rose by, calculated the density, and lo and behold, the crown maker was swindling him and was putting some of the cheaper metal in. So from that, we can now measure the shape or the volume of the stone. Now, how are we going to do that? Using the same principle. Now, I don't have all of the equipment that I should have because school is closed at the moment, so I've been improvising things. So what have I got here? I've got a couple of bricks. I have got like a broom handle thing. If I poke that through there, you can work out what's going on. And then I've got a measuring jug like that. And if I move that over to the edge of this thing here, and hoping it won't fall off. I can't really see that. I'll have to move it around like that. There we go. So you can see that now. And now what I'm going to do, put another little brick at the back, is I am going to fill my measuring jug with water. And I'm going to put as much water, so if I put any more, there it is, it's pouring out onto the table. So I'll just wait for that, catch those bits and pieces. And so I now know that that is absolutely brim full of water. And no more can fit in there. It's still a little bit dribbling out of there. So if I then put my stone in this water, it's going to make the water overflow, and not just a little bit, it's going to make the water overflow by the same amount as the volume of this thing here, because this will push the same volume of water out. So I've now got a measuring cylinder with a little funnel on the top to catch this. So I shall pop that there. I'm going to pop that in here. And as I put that in, there's water comes out of there nice and slowly. Okay, that's enough. And I've got my measuring cylinder here. And if I pop that there, I can see that the volume of this of that stone was 31 cubic centimeters. It says 31 milliliters on here. Now, a milliliter is the same as a cubic centimeter. We use cubic centimeters if we're measuring the volume of solids, and we use milliliters if we're measuring the volumes of liquids, but it's exactly the same thing. So that stone has a volume of 31 milliliters. I can measure its mass on my scales, and from that I can calculate the density. And you need to know how to calculate the density of an irregular object. Now, if I was at school, I wouldn't have such a contraption here. I would have something called a displacement can. Let's get this out of the way, and I'll show you what one of those is. A displacement can is also called a Eureka can, strangely enough, and it looks like this. It's basically a metal can with a hole in the side and a little spout, and you fill it up with water, right up to the spout, or a little bit more, so some of it drips out, and then once it's finished dripping, you then put a measuring cylinder underneath it, and the water pours out into the measuring cylinder, and from that you can calculate the volume of the thing that you want to measure. So that is it. That's density, and that's how to calculate density, the units of density, which is kilograms per cubic meter, or you can measure it in grams per cubic centimeter, which is usually more convenient, but you then got to keep your head steady and try and work out some maths and how to convert grams into kilograms and cubic centimeters into cubic meters. And you also need to know how to calculate the volume of an irregular shaped object, and for that you use a displacement can, sometimes called a eureka can, and the excess water flows over into a measuring cylinder. And that's it for density. I'll see you next time.